Hey everyone, welcome to the Rust Review. I'm Brandon Conkle. I've been a full stack developer for more than 15 years, and Rust is my favorite language because of the predictability and determinism it brings to my programming. On this show, I sift through articles and topics from different sources to find interesting things to share with you and let you know what I think about them. If you've got an article you'd like to see featured on the show, let me know in the comments or in the Rust programming language Discord, where I hang out as B. Conkle. I'm a little late this week, and I only have myself to blame for it. I decided to install Arch Linux for the first time, and I got caught up in configuring all the little minute fine-tuned things just the way I like everything. And I'm pretty happy with the result. I'm liking how it's turned out, even though it's taken some work to get there. But this is a Rust podcast and not a Linux podcast, so I'll move on. This week's episode, I'll talk about the pros and cons of Rust versus C++, what associated types really are and why they're useful, some Rust Foundation announcements and upcoming goals, an exploration of spooky action at a distance in Rust's UnsafeCell type, and some recent improvements to Doctests. All right, the first article I'm kicking things off with today is from Matthias Endler on the Corrode blog. It's called Rust versus C++, a real-world perspective. And Rust, compared to C++, is one of the primary use cases, one of the primary value propositions that you get for Rust, because C++ has long been the dominant ecosystem for low-level performance. It's when you need things where some of the high-level runtime tools slow things down too much, where performance is critical, where you're trying to shave off milliseconds. Low-level languages like C++ have always been the standard, and I'll often compare Rust to higher-level languages like Python or Java or TypeScript or something like that. And really, the value proposition compared to C++ is totally different. Whereas high-level languages, the value proposition in Rust lies more in its stability, the way that it can provide high-level features with this extreme low-level performance, and how it can solve some of the unpredictability of imperative programming, of state changes, things like that, with its ownership and borrowing system. But when you look at C++, really the value proposition is a little bit different because C++ already has that low-level performance. That's why it's been the dominant leader for so long. And so you look at what Rust can do around memory safety, especially. That's the big one. That's the one that solves like most of the biggest vulnerabilities that are really, really hard, even for very seasoned developers to consistently catch and be confident that they've eliminated from their code. But then also you think about day-to-day experience. Is it really easier to develop things in Rust, or is it harder? Is that learning curve really a factor? So Matthias sat down with Tyler Weaver. He's a co-organizer of the Boulder Rust meetup. And I have to confess, even though I live right outside of Boulder, I didn't know there was a Boulder Rust meetup. So I've already signed up for the next meeting that's happening on next Monday, and I'm excited to see what that's all about. But Tyler is a co-organizer, and he has a decade of C++ experience and several years of Rust under his belt. So he's a very good source of real-world information about what is it really like to work with Rust versus C++. And Matthias's interview, kind of, I'll say there are some biased quotes in here. I think some things that show that Tyler's a Rust fan, but I think there's good reason for it. And I'll balance it out with the Mastodon discussion that Matthias also called out and kind of kicked off in Mastodon to discuss this article and ask questions from other people who had real experience. So the first thing that Tyler talks about is how Rust is a force multiplier. He says in C++ projects, there's a lot of overhead spent just trying to get things working, just trying to get all the tools configured correctly and working together correctly. And that's beyond the time they spend optimizing and improving their code. Where he says Rust, on the other hand, it handles many of these low-level details by design. So you can focus more on your higher level concerns instead. So there are opinionated decisions made for you In C++, you'll often spend a lot of time trying to figure out what approach, what tools, what set of standards to use, whereas Rust designates a lot of that by default so that you can focus on what's different, on what really matters for your use case and the value that you're trying to provide with the code. He says that this extends to code reviews also, where he says, in his opinion, code reviews take half the time in Rust compared to C++. Because it's more obvious what's happening. There's less ambiguity, I guess. But he said they've seen a decrease by more than 2 times in the amount of effort to both build services in Rust and maintain and update those services. That's a quote from Google. Actually, Google says that C++ is very expensive to maintain, as opposed to Rust. So Tyler obviously agrees with that sentiment. He says that one of the areas where Rust shines the most is during large-scale refactoring, and I definitely agree with this sentiment that I've made some pretty major transformations of the Rust code bases that I work on in my side project time. And even big sweeping changes I can be pretty confident in. It can take a lot of time sometimes to open up all the files and fix all the type errors and things like that, but they're all there right in front of my face for me to see. I can't move on without fixing them. It's very comprehensive and complete. Whereas in other languages like Go, for example, or TypeScript, I might think that I'm done with the refactor and then discover other places where, the type inference missed this, or the compiler allowed this even though it shouldn't have, or things like that. The Go null pointer exception runaround is definitely challenging, and I know it is in Java too. So that's one of the great distinctives of Rust. This refactoring, the soundness of its static type system really helps, and the amount of behavior encoded in the types really helps too, to make refactoring easier and more confident once you're done. He also said that in C++, removing things, even just deleting things, can be really expensive, both in terms of development time and the potential for introducing bugs, which I've definitely seen before too. Just taking something out can break everything, and you don't know until you exercise everything at runtime. Because Rust has this ownership system that ties into the compiler, so everything happens at build time. You see a lot of these issues, a lot of these production things that would typically make it out to production in other languages get caught much further up in the development process, usually during the compilation or build process. He said that on large scale projects, and I've seen this too, when you have a lot of people working in the same code, refactoring is essential. It's not a bad thing. The thing that has given refactoring a bad name, I think, is how difficult it can be in other less sound language ecosystems. But when you have the confidence that you do in something like Rust, then refactoring can become, like he said, essential for maintaining code quality and adapting to changing requirements. You can refactor frequently. You get in the habit of refactoring because the types, the compiler, the API that you're building out starts to give you hints around what you could do better and how you could structure things better. And you have the confidence that you can change those things. So I definitely agree with this. He cites an anecdote from Mozilla, how they twice tried to parallelize Firefox's CSS layout engine in C++, but abandoned both efforts. And eventually they were able to succeed using Rust in their Servo project. And it was, let's see. Oh yeah. There's another quote from Jeremy Soller from System 76. System 76 maintains the Pop! OS Linux distribution along with to go along with the Linux based hardware that they sell here in Colorado. I love System 76. They are working right now on an actual desktop window management environment to rival GNOME, essentially, for the Linux desktop, called Cosmic. So they've been doing a lot of Rust lately, and he points out that Rust gives you great tools for extremely concurrent things working with them safely. So there was no way to write the kind of code that they are in C or C++ without considerable time planning beforehand. And then I'll add considerable time running all kinds of linting and checking tools to ensure memory safety and ensure things like that. It's a pretty major undertaking in C++ to write confidently memory safe code, especially when it involves concurrency and shared memory. Another thing that Tyler points out in his responses are accidental complexity is quite high in C++. He says this it grows over time. It gradually shows up over time, making things more and more difficult to maintain over time. And there's a lot of upfront knowledge that you need to be productive. You've got to read books, you've got to watch talks, you've got to really saturate yourself in the philosophy, because otherwise you're going to get caught by all kinds of things that you don't expect, all kinds of foot guns in the C++ ecosystem. So Rust, its approach to memory management, its emphasis on explicit handling of side effects, things like that, it leads to simpler, more maintainable code structures. And again, I'll affirm this. Rust has made me a better programmer. The way that Rust forces you to think about things translates to other language ecosystems. And so I think I've become a better TypeScript and a better Go programmer because of the time that I spend in Rust, because it brings an awareness that I never really had before. Next, he talks about tooling. He talks about Rust having a significant edge in the area of tooling because it has a really great default package management and build tool called Cargo. It has a great language server protocol so that it can integrate with IDEs, things like VS Code or Vim or the IntelliJ family of products. It's able to integrate with them very smoothly because of its language server. And overall, it's a cohesive tooling environment, he says, that makes things more efficient. It makes things more high quality. It gives you, like I was saying earlier, the time to focus on what matters rather than fiddling with all of the little details and configurations and things like that. Now, obviously, as a Linux user, especially someone who just installed Arch Linux, I enjoy fiddly things. I enjoy configuring things, but not when I'm trying to get a project done. I'd rather have the right choices made for me where it makes sense, and then I can spend my time focusing on what's unusual, what's novel, what's special about my use case that I'm working on. It wouldn't be an honest evaluation unless we looked at the downsides. And so Tyler also acknowledges Rust's current limitations. He talks about the learning curve. That's the biggest thing that people talk about because it is a steeper learning curve. It is, especially if you're used to other programming languages, it's difficult to understand how Rust is different and how it does things differently. I often talk about how, object-oriented functional in the Rust world, the implications are very different, and there's less of an important distinction between the two because the ownership and borrowing tracking makes object-oriented programming less risky, and so you can embrace some of those optimizations of OOP without getting lost in the multiple inheritance mess and things like that. It has restrictions where it makes sense, but you can also use things from functional paradigms. You can use it together with OOP. It's really the best of both worlds in my mind. Some anecdotes on here. Where was it? Oh, yes. So Google cites that 2/3 of respondents are confident in contributing to a Rust code base within 2 months or less. They also say that they become as productive using Rust as other languages in 2 months or less. I would say your mileage may vary on that. It's going to take you a while to really feel intuitive in Rust, but it does happen. Just know that the onboarding and the understanding curve is a little bit different than in other languages. Another thing that he calls out is that Rust's ecosystem isn't as mature yet as C++, especially when there are just 30, 40 years of specialized libraries and frameworks and things that are in C++ that are not not available. They haven't been wrapped or ported to Rust. They're not as feature complete in Rust, and that is definitely true. Um, you can still use them in a lot of cases, but you may have to do some work to really map the foreign function interfacing and things like that. And then he also calls out that Rust hasn't achieved the same level of industry-wide adoption yet that C++ have. It's not ubiquitous everywhere like C++ is. But I think that's starting to change. You start to hear big players like Google and Microsoft. You see them talking about Rust and their plans on increasing their Rust adoption. Microsoft including it in the kernel, the Linux kernel. As you'll see, we're progressing on being able to use Rust in the Linux kernel. There's Rust in the Android stack. There's Rust all over the place. So it's growing, and to the point where some people are getting annoyed by hearing about it, but it's still not as widespread as C++ is. One kind of misnomer he called out is that a lot of people are concerned or worried about interop between C++ and Rust, but he said in his experience, it's rarely an issue in practice. And he's got a series of blog posts that talks about integrating Rust into C++ projects and handling FFI bindings and using CMake with it, all kinds of different things. So ultimately, I thought it was an interesting perspective. It felt like an advertisement, though, and I think somebody in the Mastodon art thread that I'll pull up here in a moment also called this out. It's definitely from a fan's perspective, but I think there's good reason for that. The Tyler is such a fan because of what a difference it brought to his daily life programming in a low-level environment like this. So he calls out some things about it. Ultimately, though, he says that really the benefits of Rust, they become really most apparent in your day-to-day work, in your code reviews, in your refactoring and managing complexity. It's something that I've seen too. It appears more complex at first, but as you get the hang of it, it really becomes useful. Like that complexity becomes a signal that you can use to understand when you're doing something that isn't quite right or that might lead to unintended consequences, and you can adapt. You can change the way that you're doing it, and that refactoring makes it easier. The ease of refactoring in Rust makes you more confident to be able to do that, to iterate and improve as you go. So then here in the Mastodon post, Matthias shared it and asked if there are any C++ developers who have relevant experience here that can chime in. And we got some pretty interesting results. First off, we've got Murat, who talks about how his biggest advantage that he can see, like he says, people talk about the borrow checker and low level comparable performance and things, but for him, the biggest difference is that C++, with all of the recent efforts, I assume he's talking about all of the linting and checking and analysis tools that can take hours to run against it. It just becomes, it feels half baked. The tooling became harder to maintain. He says it's too broad, it's too complicated, and it's not very easy to share the load of all that between the devs. Whereas Rust, on the other hand, feels welcoming. It feels like it wasn't as steep of a learning curve for him because he was already trying to do these same things in C++, but it was a lot harder to maintain even with a lot of C++ experience. And so Rust helped him do what he wanted to do without all the trouble of maintaining all of that and the boilerplate code that he had to maintain. He also talked about there are some use cases where Rust falls short. It's really, like I mentioned before, the C++ ecosystem has been here a lot longer. There's a more mature libraries and things available. That's going to change with time and as people get more excited about it. But ultimately, he says, Rust decreases my tech debt and stability anxiety. And Matthias liked that. He said stability anxiety is a nice way to think about it. That's definitely how I feel about TypeScript and Go sometimes too. Just like, I think I've done everything right. I think I've checked off all the boxes, but there's still surprises that could hit. And I don't like that. And I have not had that same experience with Rust. Providing a opposing perspective, for the most part, is another respondent, Ananas. They use both Rust and C++, and they say it's not either or. It's pick a tool according to your project and your use case, essentially. Said in Rust, concurrent code is significantly easier, and it doesn't have a lot of the same baggage that C++ does, but really it depends heavily on your project. If you're writing a lot of low-level stuff and it's trivial to make it concurrent already in C++, then Rust isn't going to give you much. But if you're writing something where you'd spend a lot of time thinking, how do I make this thread safe, then Rust is extremely helpful. Both languages need test suites anyway for extensive refactors, he says, and that I agree with. I would say he says the quality of the tests is more important than the language features. In my opinion, the language features help you not have to write as many tests. Your tests can be more focused. They can cover the things that the language features don't handle. And so there's less lifting done in the test suite, I think, even though he's right. The test suite is still required in both cases. There's no programming language that will magically reduce or remove the requirement for testing. And he points out as a downside, he says you will refactor a lot more using Rust. I contend that that's actually a good side, a good thing, that you can refactor a lot using Rust because you see better ways to do it, and you can do it without the stability anxiety we were talking about. Check out the thread for the full details. There's some good discussion here. Matthias responds saying that the part he likes most about Rust's tooling is that it's opinionated. Decisions are made. Like I was saying earlier, in C++, teams can argue about the best way to do things for a long time. And Rust provides everything you need up front and gives you the one right way to do it. That's one thing that I always liked about Python's perspective. What is it, the Tao of Python or something? It's been too many years, but there's a great perspective on the Python philosophy that talks about how there should be one right way to do things. There should not be a million different variations. There should be one way that is generally accepted as the right way, unless you need like special cases or things like that. That's kind of the philosophy of Python, is to provide the right way to do things, and instead of fracturing into a whole bunch of other things that are competing. And it may be more or less successful depending on your opinion, but I think that's how we should approach things in Rust too. Instead of building a bunch of different competing implementations or things, we should focus on the right way to do things. We should focus on opinionated solutions, and yeah. And he also Matthias calls out that refactoring isn't necessarily a negative thing. The key is to make refactors a normal part of your development cycle. And he says Rust is really great about that. Ananis calls out that he doesn't think it's that simple, but there's some great discussion. Definitely check it out. One thing that he does acknowledge is that even though the learning curve is steeper than C++, it's more smooth. It's more consistent. And he says the language is a great deal more teachable than C++ is, because there's so much like tribal knowledge around C++ that you have to learn to really be effective with it. I liked this quote. I'll leave things on this from Eric Scooten, who says, C++ defenders often point out that you can write memory safe C++, and that's true, but it's rarely obvious that you've done so. And I like that perspective a lot. All right, next up, I'm going to talk about associated types. This is an article from Gavin Gray called "Fear Not: The Association of Types." Love the dramatic title for it. So associated types are actually a really strong feature of Rust. This is one of the features of Rust's high-level type system, and it's a great developer experience that I think really contributes a lot because it really helps with strong inference. That's one thing that in Java, you don't really get that benefit. You don't see inference. You have to provide type annotations everywhere. Whereas the associated types of Rust actually gives it a lot of clues that gives it the ability to infer quite a bit. And so it makes things a little bit less verbose and more reliable because it's reading between the lines. It's looking deep into the behavior of your code and making sure that it fits together consistently. So Gavin's article was prompted because of his assertion that Rust associated types are misunderstood. And he backs that up by talking about a recent, let's see, in the Rust book experience from Will Crichton, and he talks about questions that were posted about associated types, and many of the questions involving associated types on traits were answered incorrectly. And he wants to provide some clarity there and to really push the idea that associated types are no more than the return of a type level function, which might be confusing if you haven't dealt with languages with strong type systems that have type level functionality. Then you might be confused, what is a type level function? But if you've worked in TypeScript and you've done things where you're transforming keys or you're manipulating the data that's carried in the types rather than the actual behavior, the runtime of the language itself, that's kind of the type level functionality that, you can have certain types dependent on other types. You can have transformations that you do with your types. Those are all type level behavior. That's all code that gets executed at build time in order to establish the framework of the types that the compiler is using to validate the program. So Huey's going to talk about what that means and how that works. And to start off with, he's going to use multiplication as an example. And so traits are the way that Rust handles polymorphism. So you'll have some languages like Go, for example, before a couple of years ago when it got generics. If you wanted polymorphism, it had to be all runtime through reflection, and anything that was static, there was no way to overload operators or to make a function work with multiple different types. And the way that Rust handles that is through traits, where you can declare that in order to implement a trait, a struct or an object can make sure that it provides these methods, and whatever the state is behind the scenes, whatever internal properties these methods are using behind the scenes don't matter. That's part of the implementation details. It just needs to exhibit this behavior. It needs to have this interface of methods that can be called on it. And you'll notice this trait has something other than a method signature here. It also has a type. So that is an associated type. So he talks about how there's a lot of behavior, a lot of what Rust does that's implemented through traits and associated types. It's definitely one of the strongest features of the language, I think. So what are they? Why are they needed? Why is output an associated type here? And why is RHS for the right-hand side? Why is that a type parameter and not an associated type? So he says, if you can answer these questions well, the API of your future Rust libraries will be structured well, and I look forward to using them. I like that. So looking into his example here, he decides to provide a bad multiplication that has the right-hand side and the output as type parameters already. And in his explanation here, he calls out something that is not immediately obvious. If you look at this trait here, it looks like it has 2 parameters, but it actually has 3 type parameters. There's self, which is implicit. Self is an implicit type that refers to the thing that is implementing the trait, or the type that's implementing the trait. And then right-hand side and output are the explicitly defined parameters. So self is an implicit type parameter to every trait, and it denotes the type for which the trait will be implemented, he says. So in this case, if you look at an implementation of that bad mul trait that he's defined here, you'll see what he means, because this right here refers to self. So when you're saying impl whatever for whatever, that is the for type is the self parameter. And then obviously he's passing I32 for the other 2 parameters explicitly. And so he calls out, this looks fine at first. This looks like it's not a problem. But he says, let's take a breath and jot down some of the types that we could substitute for our parameters. And so he starts talking about, the different available options. And he says, no, if you thought that looks about right, then I'm about to shatter your world. The above is wrong. One of these lines is not like the others, and it's the output line. The output line there, if you take, for example, an I-32 multiplied by an F-32, it's not going to result in a two-dimensional matrix. It's going to result in a float. So what went wrong here? This is legitimate. You can pass matrix I-32 as the output type. But the problem is that that's not going to work because the type for output is dependent on the actual types for self and RHS. So we can't choose any type for output. We're not free to choose the type. Once we've chosen self and RHS, then there exists one natural choice for output once the others have been fixed. So output is dependent on self and RHS. And so that dependency between those type parameters, that's the important part here. If such a dependency exists between type parameters, the dependent type parameter should become an associated type. Because as he goes on later to talk about the self and the type parameter, they map to one possible output type. So here is an example of what it would look like with the actual, with the associated type wired in. And so you can see, you would say type output equals F32, because if you're multiplying a float and an integer, then the output is going to be a float. So there's one right answer here and one type that it could be. That's the distinctive. That's where associated types really shine. And because of that relationship, because of that mapping, that's what helps the compiler infer things much more confidently. So let's think about this. What if, let's see, I'm trying to remember which part he moves on to here. Oh yes. What if RHS was an associated type? So that's the next question. If output is an associated type, it's dependent on the other two types. What about right-hand side? Would that be dependent on the type of self? So he says, to help you decide, let's try it out. So he says, let's think about the things that we could assign to the right-hand side. If self was a vec I-32, then what could you assign RHS to? It could be an integer, it could be a float. Could it be another vector? They say no. You can't have a vector of integers multiplied by a vector of integers because it's ambiguous. If you use the multiplier operator, which is what this trait powers behind the scenes, this is the trait that powers that multiplier operator. Multiplication between vectors could mean element-wise multiplication. It could mean an inner vector product or an outer vector product. There's different ways that you can combine them together. And he says some languages, some libraries will just default to one way, but really it's not one right answer. There are multiple ways that you could apply it. So he says, yes, right-hand side is dependent on self, but should it be an associated type? Because there are multiple answers to what it could be. Our right-hand side it doesn't map to one right answer. It maps to a reduced set of possible answers. And so he says that means that it should not be an associated type. And so he illustrates why by creating a trait that has both right-hand side and output as associated types on it. And he provides a couple of implementations for it. So he's implementing restricted mul for an integer, but then the right-hand side is an integer, so the output, therefore, is an integer. And then he implements restricted mul for an integer where the right-hand side is a float, so therefore the left-hand side is a float. And at face value, at first, this seems reasonable. This makes sense. But as he points out, it won't compile. It fails to compile because there are conflicting implementations. If you look, it's implementing restricted mul for I-32 twice. Even though the associated types are different, Rust doesn't know which implementation to pick based on what you're doing. So he says the core issue is that for one left-hand side type or self type of I-32, there are multiple types that we might want to assign to the right-hand side. And When a type is an associated type, it signals that it can be instantiated with exactly one type per implementation block. So this is multiple implementation blocks for the same type using different associated types, and that's not how it works. You can only have one implementation for that self type, so that Rust knows exactly what function to execute. And he goes on later in the article to talk about the difference between Java. Java doesn't have that same restriction. Java doesn't have associated types, so it just uses type parameters, and it figures out which actual function address to call at runtime. It has some runtime code that exists to figure out which actual function address to call based on the types that are being passed in. But Rust does not have this kind of runtime support, and that's on purpose. That's by design. And so associated types are a way to help it do this at build time rather than at runtime. So to explain more of this, he steps back a minute. He says, let's forget about static types for a moment. Let's write it in a dynamically typed language. He uses Julia. So he runs through the same kind of example. What could the possible values of these variables be? And again, we see that the set for C is not the same as the others. The value of C depends on the values chosen for A and B. And so there's a mapping. There's a table that maps it. You can see, if A is 2 and B is 3, then output is going to be 6. And so the type, the value is dependent, the output is dependent on the inputs. And so purely functional, this is what we go for. There's no external variability involved. There's no chaos. It's these inputs always lead to this output. And that's what we're looking at here. But if you step back a little bit and you look at the types, you can see it works the same way. So integer times integer equals integer, or integer times float equals float. Like you have that same kind of association, that same kind of direct mapping that you always know what the right answer is for the output type. And so he says this is the behavior that he calls a type level function. You provide two input types and you get back an output type. So just how functions on values take input values, the parameters, and they return the output value, the return. This is input types, and you get an output type, which is the associated type here. So for traits, the same type parameters always map to the same associated type. That's what the distinctive is here. The compiler can guarantee this, and that's what the compiler uses to gain the confidence to infer things later on. It can statically guarantee that for two input types, there's only going to exist one implementation of the multiply method, so it knows exactly which address to invoke for this function, and it doesn't need runtime support like Java does. So I'll gloss over the rest of this article here. It's definitely interesting. It goes into more detail about the why things are this way. It goes into why item is an associated type in an iterator, because again, for all of the types that self could be in this case, there's no parameters here. It's a little bit more confusing than the more straightforward examples before, but each one has a single specific type for item, the output type there, the associated type. So that mapping, that table exists in this case too. So like I said, he goes on to talk about Java. He talks about why Java is different and the downsides to that. But the Rust compiler needs to know the exact address of the function to be called. There's no runtime to figure it out. And so associated types helps it get there in a way that provides a good developer experience. So he summarizes, he follows up by saying, again, his rule of thumb, and I like his rule of thumb here. It says a type parameter should be an associated type if for all implementation blocks, there exists a relationship mapping the other type parameters to it. So you can create a table mapping the other parameters to the associated type like they did for mul. So the important difference is that associated types can be specified once per implementation, and then type parameters can vary. If you've been confused about associated types and how they're helpful, this is a great article to break that down and to show what it would look like if we didn't have them and the downsides that we would have. Essentially, it would mean we would have to explicitly annotate a whole lot more, and our code would become a lot more verbose, and there would be more opportunity for human error there too. The Rust compiler does a whole lot to prevent human errors, and this is one of the ways that it does it. All right, I'm going to shift gears and do a few announcements pretty quick here. The next article is announcing Rust 1.80.1. So 1.80 is a rather big release. 1.80.1, however, is a pretty small release. It fixes two regressions that were reported. First is a problem when comparing floats. There's there's an optimization. So Rust.1.78 added an optimization called jump threading, where it's able to merge together two adjacent branches that perform the same comparison. And so they can optimize that into just one comparison. But in order to do that, it has to determine when it can't do that. And there was a case where it shouldn't have been optimized, but it was a false positive, and it was being applied to these float comparisons. So they fixed that. It also fixed some false positives on the dead code linting. So not a big release, but definitely a couple of things that will improve your quality of life as a Rust developer. They go on to this is Nico Matsakis talks about Rust's goals for 2024, and I like the direction that we're heading here. The article kind of outlines how they sat down and selected a slate of project goals. They're using this new road mapping process, and so we'll see how that goes. So this is roughly a 6-month cycle or iteration that they're targeting 3 flagship goals and then 23 other secondary goals. The flagship goals are what they call their most ambitious or impactful efforts. They're going to finalize preparations for the Rust 2024 edition. So we're getting a new edition, which is not a everyday thing. It's been every few years, really, I think. And they're also going to focus on the async Rust experience and bring it closer to parity with synchronous Rust. This is a big one, I think, especially as Rust begins to gain more adoption and saturation in web-based or API-based networking kind of contexts. The async is going to be more and more important. So bringing that experience in line with the quality of the synchronous Rust ecosystem is one of their big priorities. They're also going to focus on the Linux kernel and resolve some of the blockers that are preventing it from being a real production option for building on stable Rust in Linux. So they talk about why they chose these goals. They talk about how the 2024 edition is a way to correct small ergonomic issues that they call with Rust to make it overall a lot easier to use. I think these are small changes that'll have a big impact. They talk about some interesting things. So they're going to support impl-trait and async function in traits, which has been supported with a shim right now. So it'll be nice to see that stabilize. There's also some work to reserve the gen keyword so that we can start to get async generators in the future. That's interesting. Generators is a big feature in other language ecosystems that has been absent in Rust. So I'm excited to see that move forward. And then also some changes around the never type, the exclamation point type. So there's good reasons behind that, I think. For the async support, they're focusing a lot on async closures, which are the inline functions, and they're a little bit tricky for async right now. And then they're also going to, like I said, raise the experience of authoring async Rust to the same level of quality as sync Rust. because async is now widely used. They in the 2023 Rust survey, more than 50% of respondents indicated that they use Rust to build server-side or back-end applications where async is often a primary concern or requirement. And then supporting Rust for the Linux kernel, we have experimental support right now, and it's exciting. It demonstrates, like they say, to the world that Rust is capable of handling these low-level systems applications that have long been relying on C++, but it's not ready for prime time yet. There's a number of unstable features. It's not really in a place that it can move beyond experimental status right now. And so that's going to be one of their big goals, is to remove that blocker and to support the continued rollout of async by making it a lot easier to use, hopefully addressing some of the concerns I talked about in last week's episode. All right, so definitely an interesting post there about where Rust is going. And then an interesting aside talking about Rust's kernel support in Linux. They just announced that the documentation, the Rust doc generated documentation, is now available. They now have a homepage for it. It uses a specific kernel configuration, so it's based on the x86-64 architecture. So it might be slightly different for ARM or for RISC-V or something like that. But generally, this will give you a good baseline understanding of it. And I think you can most likely regenerate it locally with other configurations to see what's different if you need to. But I think a lot of times the type hinting in your IDE will help you in that regard. But the actual documentation, that was the announcement that I had pulled up on the mailing list, but the actual documentation is here. And it's definitely interesting. I'm fascinated by this, and I think I might want to jump in and try some ARM work in Rust soon. So this is definitely interesting to me. All right. This article is fascinating to me. So this was written by Leon Sherman. He's a PhD student at Princeton. He goes in depth and analyzing some rather surprising behavior that he encountered with UnsafeCell and atomics, and kind of talking about synchronization and the underlying assembly code that Rust generates that can have some pretty surprising or behaviors that'll catch you off guard. So this is mainly an exploration of unsafe Rust, and to me, this really points out, man, this is what Rust is saving you from. When you override Rust's protections, when you try to take matters into your own hands, it becomes really tricky and complicated, and you have to have an understanding of the assembly code that it's generating to really effectively and confidently use it. So it starts to drift off into C++ territory in that case. So Leon's blog post, I will admit, it goes beyond my full understanding of assembly language. There are some things in here that I get the general idea of, I get the gist of, but I don't totally know how to read the assembly perfectly. But it's still really fascinating. So he talks about Rust and its governing rule about shared references. So at any time, a value may have either multiple immutable shared references or a single mutable unique reference, and never both. That's part of how it helps protect against unpredictable behavior, and that's what the ownership tracking does. So the concept that he's talking about is aliasing is mutually exclusive to mutability. You can have one or the other, but not both. So in this post, he talks about how types like UnsafeCell or cell or mutex or things like that, how they interact with Rust's type system. If you look at a mutex or a cell or something like that, you'll see that it's built on unsafe Rust. And so he tries to build similar things in unsafe Rust and gets some weird results and digs in to understand why. And the results are something that you will definitely want to dig into and understand in greater detail if you're planning on using unsafe Rust in any way. This is the kind of stuff that in a code review, you've got to pay special attention to, because if there's unsafe things going on, then it could be very tricky behind the scenes, and you've got to have an awareness of all the ways that it could go wrong. So his use case that he implements is an atomic usize, uh, which is an unsigned integer, could be 32-bit or 64-bit, depending on the environment that you're in. So he's working on an AMD 64 CPU, and so he implements his own atomic usize using an unsafe cell, carrying a usize inside of it. And so he talks about how he defines the atomic usize to be a wrapper around that unsafe cell that allows us to modify its contents, even if we hold just a shared reference to it. So this is interior mutability. The usize needs to be within an unsafe cell to effectively opt out of Rust's borrow checker, he cites from William Henderson's post. And so this is the distinctive thing about an unsafe cell, despite allowing interior mutability, and despite allowing that it doesn't perform any kind of synchronization. It's not like a mutex or an RW lock or something like that. It skips that part and it leaves it up to you. And so now it's your responsibility to make sure things are properly synchronized, or concurrent access is prevented, or all of that kind of undefined or unpredictable behavior that Rust is supposed to guard against, you're opting out of with an unsafe cell. So if you don't have this trait, then you can't share a reference to this type between threads. So, I'm sorry, if you don't have the sync trait, which UnsafeCell does not implement. So one of the things that Rust does is guarantee that it's not going to have unsynchronized accesses because of that sync trait. And so you have to wrap it with something. And so that's what this atomic usize is doing. And you'll notice it does an unsafe implementation of the sync trait. So when you're doing this, when you're writing unsafe code like this, you're taking responsibility for the things that the compiler usually takes responsibility for. So with the compiler, it's preventing you from doing things that it can't prove will not cause a problem. And in this case, you're saying, all right, I can be reasonably sure that this won't cause a problem. So compiler, just because you can't prove it doesn't mean you shouldn't allow it. Unsafe opts out. It's the escape hatch that allows you to take responsibility. And he points out how this can bite you. So in his atomic usize, he starts to play around with different things in a main thread. So he creates the shared atomic. He starts up a reader thread and spawns the reader with this shared atomic clone that he made of it. He waits for 50 milliseconds and then calls a writer. So essentially the writer is supposed to increment the usize to 1, and then the reader basically waits until it's anything but 0. So it initializes at 0, the writer sets it to 1, and the reader basically waits until it's something that's not 0. So once the writer is called here, once you join the thread back again, once you synchronize with the thread, it should exit. It should say, okay, the writer's done. It's now 1. The while loop is over, and it exits. So in a debug build, when you're just working on it locally, it does exactly what you would expect. It runs for 50 milliseconds for the sleep, and then it exits because the writer immediately sets the usize to 1, and the thread is joined and finishes. It completes and exits. But if you compile it in release mode, the program doesn't quit and fully consumes a CPU core while it's running. So infinite loop, something's clearly going wrong. Why? In order to find out why, you've got to dig into the assembly. So he talks about how you can use the Rust playground to take a look at the underlying assembly that Rust generates. But here you can see it is just reading the usize once. So the RDI register it's reading from, if it happens to be 0, which it should at initialization, it'll jump into an infinite loop. This symbol here just keeps jumping to itself infinitely, because Rust determines that 0, that value that gets read, should never change because the function never modifies it. So the compiler assumes that it will always stay at this value and optimizes it out. It never returns from the while loop because it assumes the function's not changing it, so it will never change. So he says that seems to go against the whole point of UnsafeCell. It should allow interior mutability, and what's happening here is that Rust is specifically ignoring the possibility of interior mutability and optimizing it, assuming that it won't. And he goes on to provide a really minimal example that's not even based on a unsafe cell, just a regular cell, and talks about how Rust optimizes that too, even though it's being called twice. It's not, the assembly doesn't end up looking that way behind the scenes. And so he calls out, okay, if that kind of thing can happen, then what is unsafe good cell good for anyway? If you can't share it between threads and interior mutability isn't guaranteed, it can be optimized out, then what's the point? So he talks more about different ways to trigger different behavior in the resulting assembly code. And so he adds a call to a writer in between, which could be any kind of dynamic function, and calls out how this changes the assembly that gets generated by Rust. All of a sudden, there's a lot more happening. And that's because this writer function is very ambiguous. Rust doesn't know what it could do or what it couldn't do. It very well may change something. And so it makes the compiler more pessimistic in its optimizations. And that's why you get a different result here. So he calls out another way to do the same thing. And this is something I hadn't heard about, the black box hint for the compiler. The compiler, this black box hint, essentially tells the compiler to assume the most pessimistic possible operation. So it says the Rust compiler will be maximally pessimistic about what black box could do in its function argument. And it doesn't say like what it could do, but the compiler just assumes the worst. And so if you add a black box into one of those previous examples, all of a sudden it gets read twice. The assembly changes. So he calls out what this means about UnsafeCell. It's not as pure as other things in Rust because it sidesteps these kind of borrowing and ownership checking properties of Rust. And so because of that, there can be some curious behavior in the compiler optimizations that are assuming the safe operation of Rust. And because of this, he says, well, then how can things like Mutex actually work? They're implemented with UnsafeCell behind the scenes. Why do they do what they're supposed to when our implementations here don't? And he says there's a really big difference. If you look at the actual Rust atomic usize load function, you see these intrinsics. So intrinsics, atomic load relaxed, intrinsics, atomic load acquire. These compiler intrinsics hint to the compiler, just like our black box hinted to the compiler to influence the way that the assembly is generated later on. So using these compiler intrinsics, the assembly code comes out the way that you would expect it to, because you're giving the compiler more information about what could be happening here. You're cluing it in that it needs to be more pessimistic. So let's see. Yeah, it gets really into the weeds here. It's really fascinating. I learned a lot from the article. But basically, it ultimately talks about these intrinsics, these clues and hints that you're giving to the compiler, and what they do to influence the way the assembly is generated. And then he talks about Mutex, and he introduces this spooky action at a distance concept that he was talking about. And I'm going pretty long here. I'm not going to go in too much more detail about this, but basically what he found was that there's in Mutex, there's not any of these special intrinsics or hints. So why does Mutex work the way that it does? Why is it correct when our experimentations have not been? And so it really comes down to this lock method. And he talks about the lock method and how it interacts with Mutex, which is a Mutex implementation. And it uses this compare exchange function in order to operate. And so this compare exchange function, if you dig in and look at it, there the intrinsics are. That's where it's coming from. So these are the ways that in unsafe Rust, you can hint to the compiler about what might actually be happening here, what it needs to be aware of so that it doesn't optimize things out too aggressively. And the spooky action at a distance that it's talking about is in this situation, in this example, he has 2 unsafe cells that he's holding on to. So the Mutex is holding not 1, but 2 unsafe cells internally, but he's using compare exchange on only 1 of them. So you might assume that, okay, the Mutex or the unsafe cell that he used compare exchange on, that one's going to generate the assembly the way that you would expect. But then the one that he didn't touch that way, the one that he didn't use any intrinsics around, that one should go follow the highly optimized behavior that we were looking at before, where it was optimizing the behavior right out of it. But he says it doesn't. And that's because if the local, or if the intrinsics, if the hints were used on one unsafe cell within the mutex, it affects the other unsafe cell too. It becomes pessimistic, not about just the one that it was used with, but both of them. So he says, what we're observing here is that a local operation performed on one value has an implicit impact on how the compiler treats assumptions around another completely independent value. And this is really surprising. It's surprising to me too. That's why he calls it spooky action at a distance, because all of a sudden the thing that you did to this one value over here in the same context affects this other completely independent and unrelated value because the compiler just assumes the same thing about it. It's not straightforward. It's implicit. It's surprising. And it's one of the pitfalls of working with unsafe Rust. I think you really got to pay attention. You've got to look at the assembly code that it generates. You've got to be really sure, just like you are in C++, that you're not causing undefined spooky behavior here. He said, indeed, these intrinsics have implicit global effects on program behavior after compiler optimizations, and these effects do not manifest in Rust's type system at all. There's no way to tell the difference in the type level code. So this is not pure. This is not what we typically like in Rust. This is why unsafe code is so crazy. He talks a little bit about volatile cell and some of the considerations around it, but I'll skip over this. Ultimately, though, it was a really in-depth exploration of some of this weird behavior and a good illustration of why you should be very wary of unsafe code in your code reviews, in your projects. Anything that's unsafe, you've got to be really careful about. All right, so my last article today is from Guillaume Gomez. He's a prominent developer in the Rust programming community. He's been involved in maintaining the standard library and especially documentation tools, including Rust Doc. And that's what he talks about today. He talks about Doctests. So if you're not in the Python community, which I haven't really seen it a lot in other communities, you might not know what a doc test is. But he talks about how in Rust documentation, you can add code blocks like this. And when you run cargo test, it actually executes that code to make sure that it doesn't break. So it helps make your code examples more up to date, more accurate, because it'll actually break the build if your code in your examples doesn't run anymore. And it's a great feature. It's something that I used extensively in Python, and I want to use more in Rust. I just haven't as much, and I will intend to change that. But he talks about some work that he did recently on doc tests to improve the performance dramatically. So here's what he did. He says, first, he looked into how are these doc tests running? How does it collect them all? How does it gather them together? What does it do to execute them? It actually generates source code for each one of them behind the scenes. It generates tests automatically to create these tests behind the scenes and run them. And so what he found was that each doc test was compiled on its own. And that's mainly the problem. If you've got a whole bunch of different doc tests, If you look, he says, if we take a look at where live core time is spent when running its doc tests, the compile time is far and away the majority. 790 seconds, only 15 seconds are actually used for running the code. So 98% of the time is lost in compilation. But why is that the case? Why can't we combine all those together? And he talks about there's all kinds of things that can come up with these doc tests that could be a problem. They might not be using the same edition. You can specify the edition a doc test can be compiled with. Sometimes these examples are bad examples. They're supposed to not compile. So you need to have a compile fail attribute on it. And so you can't combine that with one that is supposed to compile. There's all kinds of different things that go into why you can't just easily combine them together. But in a lot of cases, you really can. So it says there are quite a lot of cases where a doc test cannot be merged with others. So in those cases, he's still compiling those on its own, just like we did before. He's focusing on the ones where you can. So generally, I would say a lot of the code can be combined together, and that's why it's optimizing things so much more. There's still some impact on the cases that can't be combined, but since they're less frequent, it becomes a pretty big improvement, I think. And he talks about how he improved that. He talks about why they require a new edition. He updated the article with this because he realized he didn't give this context. But these doc test changes are going to have to be in the 2024 edition because there are some cases where it wouldn't compile. There's cases where it wouldn't work the way that you would expect with previous editions. So this ensures that you won't have the cases that I've talked about before where code that compiled with Rust before doesn't anymore. That's one of the big things that they work to avoid. So definitely an interesting look at doc tests. It reminded me that they existed and that I need to be using them more. And great work, Guillaume, in optimizing them. We really appreciate your work in making this more useful and more valuable to the community. All right. I thought I had a shorter episode this week, but I clearly didn't. I just need to stop saying that. I need to expect it's going to be an hour or more each week. And I go on. Hopefully you found my ramblings valuable. Hopefully you appreciate my perspectives on things. If you have disagreements with me, if I got things wrong, let me know in the comments or reach out to me on Discord. Like I said, if you have articles that you'd like me to cover or topics that I haven't really talked much about, let me know. If you'd like to work with me, I would love to focus on a Rust project full time. And so if you've got work, I work with a great company called Nearform CS. We are a full service, full stack agency that can handle all kinds of e-commerce, especially code bases. We've got a specific or a special talent, I think, on the front end, but we've got a lot of back end chops too. And a lot of interest for Rust. There are many people who've gone through Rust trainings and worked on front-end tooling in Rust and things like that. And we'd love to expand our capabilities there and start to really provide some determinism and predictability to our clients with a higher quality, more high-performance code base. Let me know what you think, and thank you for watching, and hope to see you again next week.